estimating long-term flight-scale near-surface air temperature product based on the modeling output, remotely sensed data, and the observations. I'd like to present my work as the following aspects. Recently, we have heard quite reports about extreme temperature events, and this research is about the events rely on near-surface air temperature datasets. And nowadays, various methods can be used to obtain near-surface air temperature, such as in-situ observation, estimating air temperature based on the remotely sensed land surface temperature, and by the numerical simulation methods. However, each method has its limitation. For example, the remotely sensed data always discontinuous in spatial, and the modeling output product always has a very coarse resolution. So it is still a challenge to obtain a near-surface air temperature product which simultaneously matches the conditions, including covering a long-term decades, has a fire scale, for example, 1 kilometer and daily, including extreme and near surface temperature and continuous in spatial and temporal. To focus on the above challenge, we selected Yellow River Basin region as our study region, and the daily maximum, minimum, and mean near surface air temperature observed by these stations were regarded as the true data in our experiments. We know that several methods can be employed to estimate air temperature based on land surface temperature. For example, temperature vegetation method, energy balance method, and others. Among them, machine learning has been improved, always has a higher accuracy than others. But machine learning methods always need a large number of auxiliary variables. So using machine learning with multiple variables may lead to the storage and computation challenges from long-term near-surface air temperature product generation. Meanwhile, Google Earth Engine, which is a cloud computation platform, and provides abundant ready-to-use data resources. So our objectives are to explore the feasibility to estimate air temperature with machine learning or Google Earth Engine, and to test the sensitivity of variables in estimation model, and to compare the performance of deep neural network and random forest, which are the two popular machine learning methods. First, we selected 60 variables which are related to air temperature as be used in previous studies. As shown in the left table, land surface temperature is regarded as the main variables, and the other 50 variables is regarded as the auxiliary variables. All these 60 variables can be directly used on Google Earth Engine or can be easily created on Google Earth Engine. And the right figure is our flowchart. First, we create the model at point scale, and then we extended the model to graded scale to generate an air temperature product. To test the variable sensitivity, we first wrapped the 60 variables by its absolute correlation coefficients with air temperature. At the left figure is the right results. Based on the left results, we designed the cases with different numbers of input variables. For example, the first case input only involved the 3 variables with greatest absolute correlation coefficients with air temperature, and the second case involved the 4 variables with greatest absolute correlation coefficients. The rest cases were conducted in same manner, and the last case involved all these 60 variables as inputs. And this is the results based on deep neural network and based on random forest. It can be found that with the increase of the number of input variables, the R square and R tend to be stable, but the RMSE and MAE continue to decrease. Both DNN and random forest show the similar phenomena. So from DNN and random forest in our experiment, when using all variables and inputs, accuracy is highest. Besides, we have optimized the hyperparameters of DNN and random forest to compare their computation consumption and estimation accuracy. And the results show that under the same computation consumption, random forest can achieve a higher accuracy than DNN. So we say that the random forest is a better choice. Based on above, we think that it is suitable for estimating air temperature based on Google Earth energy. Uses modest land surface temperature with auxiliary variables and uses random forest model. And the accuracy is satisfactory. However, there are some missing values in the spatial distribution. And we think that the main reason is that the original modest land surface temperature is discontinuous in space. So we want to test if other land surface temperature sources can be used to estimate near surface air temperature. Here we compare three types of land surface temperature sources: the modest land surface temperature, the LST from NSAT, and the LST from geodas. And our results indicate that for mean air temperature estimation, the accuracy is similar with the three types land surface temperature. But for extreme air temperature estimation, geodas seems better. Based on the above findings, we decided to use Google Earth Energy platform, employ the random forest, and using geodas and ERA5 land products with multiple auxiliary variables to generate the seamless 1 kilometer daily air temperature products over the last 40 years. And the left table is the data we used. According to the different datasets as input, we designed four models. The first model is based on the geodas product and other auxiliary variables, and the second model is based on the ERA5 land products and other multiple auxiliary variables. For the third model, we first combined the variables from geodas and ERA5 land, and then input the combined result to the random forest model. For the last one, we combined the results of the model 1 and model 2 to generate the air temperature values. And this is a comparison of the four models based on the evaluation metrics of RMA, SE, MAE, and R-square. The model 2 seems the best for the period before 2000, and the model 4 seems the best for the period after 2000. So we would choose the model 2 to generate the air temperature before 2000, and choose the model 4 to generate air temperature after 2000. This comparison was conducted in local computer. Now we want to generate the air temperature product. So we have to move the model to the Google Earth Energy platform. And generally speaking, with more training samples, it can help the machine learning methods to better understand the relationship between input and output. But for our study, due to that the temporal resolution is daily and the study period covers 40 years, so the numbers of the samples is so large, and the size of our training datasets exists the limitation for Google Earth Energy's free users. So we designed three subsampling strategies, which called year-based, mass-based, year-mass combined-based subsampling strategy. And this is the comparison result of the three strategies. It can be concluded that for the mean and minimum air temperature estimation, mass-based subsampling strategy is suitable, and for the maximum air temperature estimation, year-based subsampling strategy is suitable. Based on the above chosen model and the strategy chosen here, we generate the daily air temperature product with the spatial resolution is 1 kilometer, which spanning from January 1st, 1982 to December 30th, 2020, and including maximum, minimum, and mean air temperature over Yellow River region of China. The product can be directly used at GE access. However, to obtain the data which is consistent with our product outside our region of periods, we provide a 1 kilometer daily air temperature estimation tool based on the trade model before, and we evaluated the tool's accuracy. The left figure indicated that the temporal extended resolution, the temporal extended accuracy is satisfactory. However, the right figure indicated that the spatial extended accuracy is lower than the original region. In summary, we developed a rapid estimation scheme for high precision spatial temporal seamless temperature products based on the Google Earth engine. And we produced a seamless 1 kilometer daily air temperature for the Yellow River region over the last 40 years. And a fast estimation tool provided to estimate the air temperature outside our region and parents. Also, there are some limitations in this work. For example, the extreme value estimation still requires improvements compared to the mean value. Besides, I think the finer scale seamless air temperature should be paid further attention. Thanks for your listening, and the detailed information about my work can be found in our 2 published papers. Thanks, and questions are welcome.
Thank you, Meiling. Do you have any questions? So I was wondering how you did your validation. So, for example, when you did you use all of the sites in training and test at those sites, or did you leave some sites out when you were predicting the air temperature?
Okay, actually, in the substantive strategy, we divided the training datasets into several mini datasets, and in each training and each evaluation, we used the tag cross validation method.
Okay, thank you. Any more questions? Yep.
I think I probably missed it. How many stations did you use to validate your model to get the air temperature?
Because the 10 cross validation method has been used, so for each time, 90% samples was used as the training data, and the rest are used as validation samples. So actually, it's the average of all samples. Thank you.
Thanks again, Meiling.